welcome all of you to this session of heat transfer. In the previous lecture, we had seen how the general conduction equation can be applied for the cases of steady state heat conduction in the spherical objects on the spherical surfaces. We had derived the temperature distribution and the heat transfer formulations for the spherical objects, and we had solved some numerical problems regarding that. So today we shall carry that discussion, and today we'll be discussing a very important topic and a very interesting topic, which is called as critical radius of insulation. Now, it is a very common idea that if you add on material at the outer layer, then it would be creating a certain amount of insulation. That means addition of insulating material on a surface will obviously decrease the heat transfer rate. So this is our common idea. Okay, sometimes what happens, this common idea doesn't hold good. So what happens in the cases of plane wall, the area perpendicular to the direction of heat flow, um, if we go on adding insulation material there, then it would always decrease the heat transfer. That means for plane walls, the thicker the insulation, the lower the heat transfer rate. Okay, so this is very simple for plane walls. But in cases of cylinders and spheres, sometimes this equation or this idea doesn't hold good. Okay, in case of cylindrical and spherical surfaces, you will see that whenever there is convection going on, okay, so along with conduction, there is convection heat transfer process is also going on. In such cases, you'll find that if you go on adding the insulation, it would increase the outer surface. That means the outer surface area is going on increasing. It is a very simple idea. The radius of insulation is getting increased. That means the area or the surface area is going on increasing. Now, the convection resistance depends on the surface area. That means the outer surface area plays an important role to find to determine the convective resistance. Okay, now as the surface area is going on increasing, the convective resistance will go on decreasing, and sometimes you will see that this is the decrement rate of this convective resistance is so high that the total resistance, the total thermal resistance is ultimately reduced. That means you know that um, heat transfer heat transfer can be defined as the ratio between the temperature changes divided by the thermal resistance. Okay, so if the total thermal resistance is getting decreased, then the net heat transfer would obviously increase. Okay, we'll be showing this whole derivations. So before the derivations, I would like to just give a brief idea so that you can understand what we are trying to derive and what is actually happening there. So the problem is that two two resistances are playing an important role. Okay, one is the conductive resistance and the second one is the convective resistance. Now, in both of these two resistances, the critical radius, the radius of insulation, this term is inbuilt there. Okay, is incorporated there. But in cases of conductive resistance, if you consider that the radius is going on increased, then the conductive resistance would increase. Okay, but if you consider the case of convective resistance, then the convective resistance would decrease for the increase in insulation radius. Okay, so there are two opposing effects going on simultaneously. Now, depending on the nature of the competition or the what we can say, depending on the values of the radius of insulation, sometimes it can happen that the ultimately you will observe that the total heat transfer rate has been increased, so which is exactly opposite to our desire. That means our objective was to insulate that material, whereas we are observing that heat transfer is increased there. So this is completely against our desire. Okay, so this phenomena, this problem can be discussed from the point of view of critical radius of insulation. So let us see what do we mean by critical radius of insulation. Okay, so let us consider a thin wall metallic cylinder which has an inner inner area or inner radius of r1, and it has, sorry, it has an outer radius of r. Okay, so this is the outer radius and this is your inner radius. Okay, now the inner surface is maintained at a temperature T1, whereas the outer surface is maintained at a temperature TO or T0, whatever you like to say. And you can see there is a fluid flow. Okay, uh, there is a fluid flow. The temperature of the fluid is T infinite. Okay, now what will happen? What are the modes of heat transfer taking place? It will be conduction as well as convection. That means both the conduction and convection mode of heat transfer will take place here. From here to here, you can see this heat transfer will be taking place, and this heat transfer would be carried by mode of conduction. And between the outer surface, that means this surface, and this fluid, the heat transfer will take place via convection. Okay, so there are two simultaneous effects. One is the conduction between the inner cylinder and the outer cylinder, and one is the convection heat transfer which is taking place between the outer surface of this cylinder and between the fluid, okay, which is flowing outside of the cylinder. Now if you try to draw an electrical circuit, this will be the methodology, or this circuit would describe the physical condition of this problem. Now our objective is that, now let us concentrate on this. So this is your conduction resistance, right? If you remember the thermal resistance for cylindrical coordinates, then this is your conduction resistance. Okay, so this is your conduction conduction resistance, and the term right next to the conduction resistance is nothing but the convection resistance. Okay, so this is your convection. Now see, if you closely take a look over the terms, you'll see in in the case of conduction resistance, this R is placed here, whereas in case of convection, this R is placed in the denominator. Okay, so in case of conduction resistance, the R is placed as a function of log, and it is placed at the numerator, whereas uh, sorry, okay, so I think you're getting my point. This R is here and this R is here. Okay, now if you think of increasing the value of R, then can you understand what will be the effect? You can think from the mathematical point of view. If you go on increasing the value of R, then this function would mathematically increase, but there would be a consecutive or the consequent decrease in this function. So there is always a competition going on between these two resistances. Now the total resistance, if you consider the total resistance, total RTH, okay, RTH is our thermal resistance. The total RTH would be ln of R divided by R1, and it will be 2 pi KL plus it will be 1 by 2 pi R L, and this is your convective heat transfer coefficient uh, at the outer surface. Okay, so this is your total thermal resistance for this physical condition. Okay, now I have already told you that if you go on increasing the value of this R, then this function would mathematically increase, but consequently this function would mathematically decrease. Okay, now to find the collaborative effect of increasing R, we need to study from the point of view of calculus. That means we need to find out a maximum or minimum value. We need to understand the optimum value of R, and then we can understand, and then we can sense it from the point of view of what we have obtained. Is it a maximum value we have obtained, or it is a minimum value? Okay, so first of all, we need to understand that we need to find out the optimum insulation thickness. So how we can do that? We can just simply uh, do a derivation with respect to the radius r. Okay, we can simply do a derivation with respect to r. Okay, now because this r is our outside thickness, this r is our insulation thickness. Okay, now if we derive this equation, then we'll find that this equation becomes 1 by 2 pi JAL. Okay, and it would be 1 by R, right? Because R1 is a constant. R1, this this whole case of insulation doesn't depend on the inner radius, it depends on the outer radius only, because this is your insulation layer. Okay, if you go on increasing this insulation up to here, then what is the change? This R1 is remaining fixed, but this R is going on changing, so we need to derive this equation with respect to R, not R1. So after the differentiation of this function with respect to R, we find that it becomes 1 by R. And if we do the derivation, I'm sorry if this is not clearly visible. I think it is 2 pi R L H infinite. H infinite represents the convective heat transfer coefficient at the outside surface. So after doing the differentiation of this function, we will find it will become 1 by 2 pi, it will become 1 by 2 pi L H O. You know that, I'm sorry, these all these terms are constant, so they are not going to change with respect to r. It is 1 by r, which would change only, so it becomes minus 1 by r square. Now what was our question here? We need to find the optimum value of this r at then we need to see if we have found out the minimum value for which the heat transfer is minimum, or the maximum value for which the heat transfer is minimum. Okay, so here after we have found out this equation, we need to do simply this. We need to take this drt dr as 0, and if we do that, then what would happen? This part would become 0, right? This part would become 0. So let us see how this uh, equation can be solved. So this is 0, that means if this is 0, then this is 0. 0 is equal to this. That means simply you can write this, right? So I'm not writing it once. Rewriting it would unnecessarily take some extra time. So here it becomes uh, okay, okay. I'm very sorry. It don't have been. Uh, it had. So if this is equal to 0, right? So if this is equal to this, then this minus wouldn't be there. So this changes. Uh, this becomes equal to this. Okay, you can do the calculations by your own. I hope you are understanding it. There is no such confusion being created here. So you can see there is some alike terms, 2 pi and this L, they are the alike terms here. And doing the simple calculation, you will find that it becomes K by H infinite. That means this critical radius of insulation, uh, I'm not I have already termed it critical radius of insulation, but this is not actually the right time to term it because I haven't told it. It is my habit that I have told it. So please concentrate here. This is the radius from where we have found that it is K by H infinite. That means this is our optimum value. Now what we need to do is to do a second order derivative. Okay, if we do a second order derivative, then we can understand we have found the minimum value or the maximum value. Okay, so this would make us much more, so it would be a convincing job. Okay, it would convince us. So after doing the second order derivative, that means d2 r th with respect to dr2, I am again not going to do the derivation or the differentiation. You can do it by your own. I'll just write down the terms which we have found out from the differentiation. Okay, it will become 1 by r square, and this term would become 1 by pi r q l h infinite. Now you know that this r is equal to k by h infinite. So here you have to put this value, and ultimately you will find this becomes h infinite to the power 2. That means h infinite square divided by 2 pi k kq. Sorry, just give me some time and I'll rewrite it here, and it would be a proper depiction of what I am trying to say here. So this is, again I have, so please be with me. I'm taking a lot of time, but so it would be 2 pi k q l. Okay, that means this is a positive term. This is obviously a positive term. Since this term is positive, then it means this is the minimum radius. Okay, so you know from the principles of maxima and minima, or the principles of maximum and minimum values, then it is quite obvious that this gives the minimum radius. Okay, so this is your minimum radius, and this represents the condition for minimum resistance, and consequently it also represents the maximum heat flow rate. So you know that heat transfer rate is the temperature difference divided by the total thermal resistance. So if your thermal resistance is minimum for this case, for this radius, then your heat transfer would become maximum. Okay, so the insulation radius at which resistance to heat flow is minimum and the heat uh, transfer rate is maximum, it is called as, this radius is called as the critical radius of insulation. So the term which I had already used, now I hope you can get it. You can understand the critical, why this word critical is used here. So critical always gives you a sense of optimal. Okay, it is a optimum sense which gives you the understanding that this is the maximum heat transfer rate which can be achieved if we go on insulating a material, if we go on applying the insulation material layer by layer. Okay, so it is quite obvious, and I hope that you have understood the clear concept of heat flow being the maximum at critical radius of insulation. Now, uh, if you try to understand the characteristics of this critical radius of insulation, we need to understand the variation. Okay, so here you can see there are two specific graphs, and they are intended for two specific cases. Okay, for the first case, you can see that this is your maximum one and this is your minimum one. Okay, so what does this R1 indicate? This R1 indicates the inner radius. That means if you go on insulating the material, then the heat transfer would become maximum, and if your critical radius is more, if your thickness of insulation or radius of insulation is greater than critical radius of insulation, then heat transfer rate would drop. Okay, so initially it goes on increasing, reaches the maximum value, and then decreases. Okay, this is the case when we are uh, so you need to understand the range of radius. Here R1 is less than RC. So this part is applicable when the inner radius is less than the critical radius of insulation. If you find that the radius have become more than the critical radius of insulation, then it would indicate the heat transfer rate is going on to decrease. Okay, so this is the second case, or when you see that, the effect of wall thickness dominates and the overall uh, thermal resistance decreases. Okay, here you can see if the radius, if the insulation radius is more than the critical radius of insulation. Okay, if the radius of insulation is uh, more than the critical radius of insulation, then you can see a heat transfer drop. Okay, so that means it, then it acts as a lagging material and it creates an obstruction in the heat transfer. Okay, I hope you have understood the fact of critical radius of insulation. It is because of the uh, two two components of thermal resistances that is important while understanding the total heat transfer rate of a cylinder when it is exposed to a surroundings. Okay, and transferring heat by the mode of convection. Okay, so I hope you have understood it. So let us see how we can derive this same thing but for spherical conditions. Okay, so we'll be interested to find out the cases for spherical conditions. Okay, here this R2, okay, it would be better if you consider this R here, because here according to this diagram this is your outer radius or the radius of insulation. So this is a sphere, okay, this is your inner radius, this is your outer radius. You can see the convection heat transfer going on, and you need to consider the conductive as well as convective thermal resistance. Okay, so your total resistance would be, let us write RT as the, so RT is your total thermal resistance, which is observed by the observed in the spherical coordinates. Okay, so what do? We just add it up, 1 by 4 pi k, 1 by 4 pi k into 1 by R1 minus R plus 1 by 4 pi. Again we need to change it. This would be only R according to the diagram, please keep in mind. So it would be H infinite. Okay, H infinite, it means the convective heat transfer coefficient for the outside surface. Okay, so now you know what do we do, what is the process. We just do a derivation with respect to the outer radius or the radius of insulation. So doing the differentiation with respect to R, we will find it would become 1 by 4 pi k, and we would like to differentiate this term only, so it would be 1 by minus 1 by 4 r square, and this term would give you 2 by 4 pi r cube h infinite. Okay, so now see, uh, you know what we do, we take this dr as 0. Okay, so this is taken as 0, and if you do it, what we'll find, we'll find that 1 by 4 pi k into 1 by r square, 1 by r square is equal to 2 divided by 4 pi, it would be r cube h o, so it would be r cube h o. Okay, or you will find this r becomes 2k, and please we have considered this as h finite, so I just missed that, and it would be, so this is your twice. So here you can see for the sphere the critical radius of insulation is twice that of the cylindrical case, 2k by h. So this is your outer convective coefficient, heat transfer coefficient. Okay, so you can do a second order derivative again and you can find the same result. Okay, so you don't need to do that step here. So and you have already understood the mechanisms and the applications of this critical radius of insulation, how this concept of critical radius of insulation can be used, and what is the importance to understand to find the critical radius of insulation. Okay, so now we would take some numerical problems so that you can understand it in a much better way. Okay, so let us start with that. A 2 mm diameter wire with 0.8 mm thick layer of insulation. The thermal conductivity of the insulation is provided here. Is used in a certain electric heating application. Okay, I think you have understood it. A 2 mm diameter wire with this thickness. The thickness of the thermal conductivity of the insulating material is given here. Is used in a certain heating application. The insulated surface is exposed to atmosphere with convective heat transfer coefficient 40 watt per meter square degree. What percentage change in heat transfer rate would occur if critical radius of insulation is used? That means uh, instead of 0.8 millimeter, if you use the critical radius of insulation, then what would be the change in heat transfer rate? That is our objective here. So here you can write this R1 as your internal radius, that becomes 1 millimeter. Okay, and this R2 becomes 1 plus, okay, I think so. I'm not doing this step, I'm simply writing 1.8. Okay, so it becomes 1.8 millimeter. So the thickness of insulation means the difference between the outer radius and the inner radius. That means uh, the outer radius would be the sum of inner radius plus thickness of insulation, right? So okay, I have done a mistake here. It would be 1.8. Okay, no, it was correct, I'm sorry. 1.8 millimeter. So it would be 1.8 millimeter. Okay, now from the first case, when the critical radius of insulation is not used, okay, let us consider the heat transfer is represented by Q. Let us take a temperature difference of delta T. So this delta T would remain constant in both the cases. That means when we are using this 0.8 millimeter thick layer of insulation, and in the second case when we would be using the critical radius of insulation. Okay, so we are talking about a cylindrical object here, or cylindrical surface here. So this is your formula: 2 pi k L ln of R2 divided by R2 divided by R1, and this is your conductive resistance. But we are still left with the convective resistance. Okay, so 2 pi H O, that is the outer convective heat transfer coefficient. 2 pi, the formula would be 2 pi R2L, that is the area of heat transfer, and this HO is multiplied here. Okay, so I think I'd like to clearly mention it here: A into HO, right? Now what is A? A is 2 pi RL. So 2 pi into HO into RL. L is the length of cylinder. Okay. Now, okay. So you can write this as 2 pi L into delta T. Okay, I'm just doing the LCM and relevant mathematical calculations. You can see that it becomes 1 by k, 1 by k into to become 1 by k. Okay, 1 by k into ln of, okay, ln of r2 by r1, right? Very simple. And in the second case it would become 1 by ho, that is the outer surface. So this is your the heat transfer rate, thus can be calculated when the 0.8 millimeter thick layer of insulation have been provided. Now if you put, now this k is simply 0.15, right? So this k would be 0.15 watt per meter Kelvin. This ho, that means the outer convection heat transfer coefficient would be 40 meter square degree. And now you can see that you have all the values you require, and after putting all the values you will see it becomes 0.0562 delta T. Okay, okay, sorry, okay, it would be into 2 pi L delta T. Okay, so this term would remain same in both the cases. Since there is no information about the length of cylinder or the temperature changes, we would consider this delta T is remaining fixed in both the cases, and it would also remain because we have to compare the cases. That means we need to compare the case. It has been also mentioned here. It may be assumed that temperature difference between surface of the wear and the surrounding air remains unchanged. That means this dt or delta t would remain same in both the cases. Now let us just keep this data here because it would be required in the later part. So 0.562 into 2 pi L into, okay, so it would be 2 pi, let us use the capital L because we are using that. So this is your heat transfer rate when this 0.8 millimeter thick layer of insulation have been provided. Now take us the second case. So let us take the second case. Let us just clear this up so it can be, now we can use or discuss the second case. Now what happens here? We are concentrated when we need to find we need to use the critical radius of insulation. So now the question is, do we know what is the value of critical radius of insulation? Yes, we do know it. We know the simple formula. RC, or the critical radius of insulation, is nothing but K by HO. So it would become 0.15 divided by 40, and ultimately you will find this value as 3.75 millimeter. Okay, so you will find the value of critical radius of insulation as 3.75 millimeter. Now how this formula would change? This radius R2 will now change to critical radius, and here this change should be incorporated. Okay, so I would like to mention, if here it was only written R, then please change it to R2 because we are talking about the convective resistance here, and it only depends on the outer radius. So please edit it, or please correct it. Okay, so this is the modified formula. I think I have done the same mistake again, so it would be RC. Okay, now you know the values of RC, right? This is already given here, and if you go on putting all the relevant values, then you will find it would become 2 pi L delta T into it would become 0.0646. Okay, so this is the heat transfer rate when the critical radius of insulation has been provided. Now what is the change? Our question is to find out what percentage change in heat transfer rate would occur if critical radius of insulation is used. So simply we can do this. This is a very rudimentary thing, and you know these things, so you just need to do this simple mathematical operation, and hope after doing this you will find that the answer becomes 14.95%. So this is your answer, 14.95%. Okay, so this is the change in heat transfer rate. So when you are providing the critical radius of insulation, 14.95% of heat transfer rate is being the heat transfer rate is increased by 14.9% when you are providing the critical radius of insulation. Okay, so I hope you have understood it. It's a pretty simple one, and after understanding this, let us see another problem. And the next problem would be almost similar, but let us see if there is some differences here. So a tube with 20 millimeter outside diameter is covered with insulation. The thermal conductivity of the insulating material is provided here to reduce heat loss so that the tube is maintained at a prescribed temperature. The dissipation of heat from the outside surface to the insulation occurs by convection into the ambient air with convection coefficient of 15 watts per meter square Kelvin. Okay, so the first question is you need to find out the critical radius of insulation, the ratio of heat loss from the tube with insulation equal to the critical thickness. Okay, so you need to find out the ratio of heat loss from the tube with insulation equal to the critical thickness, and for the thickness of insulation 20 millimeter thicker than the critical thickness. That means you need to find out the heat loss when the radius of insulation is at critical radius, and in the second case you need to find out the heat transfer when the critical radius of insulation plus along with the critical radius of insulation 20 millimeter thick, extra 20 millimeter thick insulation has been provided. Okay, so you need to calculate the two separate heat transfer rates, then you need to find out the ratio. So first we need to calculate the critical radius of insulation. So if you remember, I had already told this critical radius. If you take a cylinder here, and this is your inside surface, so this is your outside surface which has a radius r2, and this is your inside surface which has a radius of r1, and the layer of insulation is provided here. So it is very simple thickness is nothing but R2 minus R1. That means outer radius minus inner radius. Okay, so you need to find out outer radius minus inner radius. Now the question is that we need to find this critical thickness of insulation. That means this outer radius is maintained at the uh, critical radius of insulation. So this outer radius is exactly equal to the critical radius of insulation. So you can write this RC as the critical radius of insulation minus R1. Now simply we need to calculate the value of RC. We know the formula, right? And we have just used it. So it would be K by HO. Now the question is, what is the value of this K? So it is 0.18. Okay, so it would be 0.18 divided by 15, right? Very simple. So you will find that this critical radius of insulation is 12 millimeter, and then you can find, so this is your diameter, that means the radius would be 10, so 12 minus 10, so the thickness of insulation would be 2 millimeter. Now let us move on to the second question. When you have provided the critical radius of insulation, you need to calculate the heat transfer rate. And in the second case, the radius of insulation is 20 millimeter thicker than the first one. Okay, so let us see how it can be done. But please remember, okay, just write it here so that we can remember this critical radius of insulation. And let us take this thickness. Okay, I know I have a very bad handwriting, but please read it. Okay, so this is uh, these are the fundamental questions which needed to be answered, and then only we can move on to the second step of the problem. Now let us consider the insulation case. Okay, mm, so when when the insulation is given to you with insulation. Okay, so let us see how the formula can be written here. So the question is that you need to compare the heat transfer rates when the critical radius of insulation has been provided and there is no insulation. Okay, so you need to understand the two specific cases here. You need to find out when the critical radius of insulation is provided, then what is the heat transfer rate, and if no insulation is provided, then what is the heat transfer rate. Okay, so this is the heat transfer rate with insulation. Here you can see I have already replaced this R2, that was the outer radius, by RC, and you know this RC is 12 millimeter. Okay, so this is your conductive resistance and this is your convective resistance. This is for the outer surface, the convection taking place between the outer surface and the ambient air. Okay, and this is your conduction within the T. So if you just simplify this equation, then it will become 2 pi RC LHO into T minus T0 divided by RC into HO by K, plus this is simple algebra, you will easily understand it. Now if we do a simple calculation, then it would be Q width by Q without. So the result would be it will be simply given as RC by R1 RC by R1 into this part here. It would be RC again into HO by K plus, I'm sorry, it would be something. Okay, uh, there is a misplaced formula. I would like to mention that. Please change it. There is a calculation error here. It would be like this. Okay, then this could be written here. So it would be into ln of RC divided by R1 plus 1 and to the power minus 1. That means RC by R1 divided by this term. Okay, if you do the calculations without, and now here all the terms involved, you have a proper value of these terms, all the terms you know. So if you put all the values, this K would be 0.18 watt per meter Kelvin. So after putting all the values, you will find this ratio would become 1.105. Okay, so this ratio would become 1.105. Sorry, again it would be 0.15, 1.015. Okay, so you can see heat loss is increased by 1.5% despite the fact the 2 centimeter thick insulation cover is provided. Okay, so you can see the heat loss have been increased by 1.015% despite the fact that 2 centimeter thick insulation cover up has been provided here. Now coming to the second question. For the second case, it has been mentioned that the thickness of insulation is 20 millimeter thicker than the critical radius, okay, or the critical thickness. So that means what will be the uh, critical what would be the value of the insulation or the thickness of insulation? Initially it was 12, then you add up 20 millimeter, so it would be 12 plus 20. Okay, so just writing here RC2. Okay, so this is, though sorry, this is not the critical radius of insulation, mind it, so I won't use the suffix here. So just writing R2 here, and R2 is 32 32 millimeter. Okay, so R2 is 32 millimeter. Now let us do the same calculation again, but here we need to put okay, first of all we need to understand that this RC should be replaced here. This RC shouldn't be present here. So instead of RC, we need to put R2 here. Okay. So, but the basic formulation would remain exactly same. So RC, again RC here. This is RC again, and this is RC again. Here there would be RC, and here, okay, I'm sorry that I have done this thing. I have done exactly the opposite what I am trying to say, but please consider here, please try to understand that this, instead of RC I meant 32. Okay, so okay, I would do it. I meant R2, but I have done RC, so I will rewrite it. Okay, so it is taking time because of a silly mistake, so please so it would be R2, it would be R2, it would be R2 again, this would be R2, here this should be R2, okay, and this would be R2 also. Now just remove this. Now the formulation remains same, but the problem is that this R2 have been changed. So this R2 has changed to 32. So now if you put R2 as 32, R1 as 10 millimeter, this HO as 15 watt per meter square Kelvin, this K as this, remember that this K is 0.18, and please remember that this is the inverse sign. Okay, so if you do the calculations, you will see it would become 0.78 in the second case. Okay, so you can see that the heat loss, that is the ratio, that means the heat loss decreases by 22% when 22 millimeter thick insulation is provided. Okay, 20 plus the thickness of insulation was 2, so 20 plus 2, 22 millimeter, so this is 78, that means 22% of decrease in heat loss, 22% of decrease in heat loss if if 22 millimeter of the thickness of insulation has been provided. Okay, so this was a very simple problem. It was just understanding the problem and putting all the details. Okay, so with this I would like to end this lecture here, and in the next lecture we should discuss about the again we'll be discussing about the one dimensional steady state conduction equation for plane walls, spheres, and cylinders. But in the next lectures, we would consider the internal thermal energy generation. That means we would accept the fact that we will consider those cases where there is some uh, thermal energy generation is taking place. Okay, so till then, goodbye and thank you all of you.